The lesson we're going to talk about related to energy is the concept of power. So to introduce that idea, I want you to think about this scenario. We have these two cars here. We have a very nice sports car and this old ratty beat-up car over here. And I want you to think about who would win, or which car would win in a race up a mountain, or which car would win in a drag race. And let's think for a second about this idea of kinetic energy. Kinetic energy is 1/2 mv squared. Now, if we think about these two cars, their masses probably are not going to be that different. Okay, they're about the same size. This one looks like an old clunker here. Their masses aren't going to be that different. And if they both get up to a speed of, say, 60 miles an hour, okay, their velocities are going to be the same too, which means their kinetic energies are going to be basically the same. Right? So if they're speeding up, they're going to reach basically the same kinetic energy eventually. Right? Here's the question though. Why do people pay lots of money for a car like this? And the answer is time. Okay, that's the key difference. This car is going to reach that speed in less time. This car is going to gain that kinetic energy in less time. And that's really what power measures. So power is all about how quickly the energy changes, the rate of change of power. And as we saw on the last slide, just about any car can get to 60 miles an hour. So they're all going to be about the same energy, assuming their masses aren't that different. But more expensive cars take a lot less time, because those cars have a lot more power in their engines. All right, so that's what power is all about here. The unit we're going to use for power is the watt. Okay, you might have seen this unit before, especially if you're changing light bulbs. Light bulbs are also rated in terms of their power, the number of watts of energy that they consume. And a watt is simply a joule per second. Okay, that's the definition of a watt. So if you have a 60-watt light bulb, it means it uses 60 joules of energy every second. Horsepower, obviously, is a unit of power as well that we typically use when we're talking about cars or other pieces of machinery, but it's not the standard unit. 1 horsepower is about 746 watts, just for reference there. Equation-wise, the average power is simply the work divided by the time. Keep in mind that there are 3 ways of finding work. So you're going to have to think about what information you're given and decide exactly how you're going to get the work done in a particular problem. All right. It is average power, as you note, because it's simply the work over a period of time. If we wanted instantaneous power, we'd have to do calculus, we'd have to do a derivative. All right. We're going to focus just on average power for this class. Let's do a few conceptual questions here with power. So for this first one, we have 2 cars with identical masses, and they're both speeding up. One speeds up from rest to a speed of 10 meters per second. The other goes from 10 meters per second to 20 meters per second. So the first question is, which car experiences a greater acceleration? The answer here is that they are going to experience the same acceleration. So if we think about our equation for acceleration, it's really v final minus v initial over t, the change in velocity over time. These cars experience the same change in velocity over the same period of time, and therefore they must have the same acceleration. For the second one, if we think about which car has a greater power output, that's going to be car B. And when we're thinking about that, we think about the fact that power is simply work over time. And in this case, our work is resulting from a change in kinetic energy. All right? And our kinetic energy is 1/2 mv squared. So we can say that change is 1/2 mv final squared minus 1/2 v initial squared. So if we want, we can go ahead and plug in some numbers here using 0 and 10 as our speeds for car A and 10 and 20 as our speeds for car B. We can go ahead and work out what the change in kinetic energy or the work done would be for each one. And when we do that, we see that car B clearly has a greater change in kinetic energy and therefore a greater amount of work done. And that makes sense. And the reason why that makes sense is because with kinetic energy, that V term is squared. So even though they have the same change in velocity going from 0 to 10 and 10 to 20, the fact that that velocity is squared means going from 0 to 10 squared is not the same as going from 10 squared to 20 squared. And that's why car B ends up having more work being done on it, and therefore it has a greater average power output during this time. Moving on to this next question, we have 2 boxes here. They're pushed across the floor with the same force F. The one box, box A, has twice as much mass though, and we want to know which one has more average power provided to it while being pushed over a distance of d. So this one's actually going to end up being box B, and what we want to think about here with this one is, once again, that power is work over time, and our work done here is going to be F delta X cosine theta. So because these two boxes have the same force acting on them, they're pushed over the same distance, and the angle is going to be 0 in both cases, so cosine of 0 is 1. They're going to have the same work being done on them. It's the same force, same distance, so same work is going to be done. However, this box here has twice as much mass, which means it will have a lower acceleration, and that means it's going to take more time to push box A across the floor. And so that means that the power will be less. Okay, so even though the two have the same amount of work being done on them, it's going to take box A a longer period of time to move that distance d, and therefore the power for A is going to be less. Let's do a few math problems with power here. So each time we're always going to start with the fact that average power is equal to work over time. And what we really want to think about is how we're going to find work in each one of these situations. So in this case, I have a force and I have a displacement, which means that I'm going to find my work by doing F delta X cosine of theta. So I know my force is 5,000, my displacement is 3.5, and the angle here, I'm told, is that the force blows at an angle of 15 degrees relative to the motion of the boat. So that's going to be the angle between the force and the displacement. And so I get a work done here of 16,904 joules. Now that I have that, I can use the time that I'm given, and power is just going to be that work over time, so 16,904 all over that 4 seconds, and so I get a work done here, 4,226 watts. Moving on to this next one here, I'm going to start once again with the fact that power, or average power, is equal to work over time. In this case, I'm going to think about how I find my work, and my work is going to be my change in energy here. Okay, I know some things about the change in energy of this car. It starts from rest at the bottom of a hill. It goes to the top of the hill and is traveling at some speed, because that's what I'm looking for. So we have a change in both the potential energy and the kinetic energy of this object. So I'm going to say that work is that change in energy, my final energy minus my initial energy. So what I end up with is gravitational potential energy and kinetic energy. Those are both my final energies. My initial energy was just 0. I was at rest at the bottom of a hill. So I can say that my work done here is going to be mgh plus 1/2 mv squared. I can plug in the values I know for that, although I don't quite yet know my velocity term. So what I end up having here for work is that work is going to be 132,300 plus 750 v squared. So I can now use some other things I know to go ahead and solve for that v. So I know my power output and I know my time. So let's go back here to our power equation. So my power here is 50 kilowatts, or 50,000 watts, and that's going to be equal to that work that I just got an expression for, 132,300 plus 750 v squared, all over my time, which is 4.5 seconds. So I can go ahead and multiply by 4.5 and subtract that 132,300, and what I'm left with is 92,700 is equal to 750 v squared. And when I go ahead and solve for my velocity, I get a speed here of 11.1 meters per second. For this next one here, we have a car traveling down a level road at a constant speed of v, and there is air resistance exerting a backwards force of F on this car as it's traveling here at this speed of v, and we want to know how much power the engine needs to output in order to keep the car moving at a constant speed. Well, in order to do that, we need a forward force of F to equal out the backwards force of air resistance, so our acceleration stays 0. So let's go ahead and think about power. Okay, once again, power is just going to be work over time, and in this case, I'm going to be using my work is F delta X cosine theta. in order to set this up, because I know the force. I don't know a ton of things here, but I do know the force. So I'm going to go ahead and plug this in here. So I'm going to say power is F delta X cosine of 0. I can say it's 0 because my force is going to the right. My displacement is also to the right, so that angle is 0 all over my time here. Now, I don't know displacement, I don't know time. However, I do know my velocity. If I'm traveling at a constant speed where my acceleration is 0, that means that my velocity is simply going to be equal to my displacement over my time. And so this term here, delta x over t, is actually equal to that velocity that I know. So I can say power is simply F times V times cosine of 0. And this actually is a roundabout way of deriving the instantaneous power of an object, okay? This is not something that you're expected to know off the top of your head, but you should be able to do a problem like this where you're walking your way through it to lead ultimately to this derivation.